Okay, so it's great pleasure to have Aswin from Rutgers and Bangalore. He's going to tell us about family and the Hitchin system, family of Hitchin system, and equal to theory and Deligne-Simpson problem. Please.
Thank you, Satoshi. Hello to everyone. Thanks for joining in to listen to the seminar. So my talk is going to be about a paper that I recently wrote with Jacques Distler and Donagi. And the title of the paper is Families of Hitchin Systems and N equal to 2 Theories. And along the way, we also found an application to the Deligne-Simpson problem. So I'll try to also talk a bit about that. So I'll start with some quick overview of the circle of ideas that we have been thinking about. Um, so Hitchin systems have often appeared in recent literature on supersymmetric gauge theories. You can, for example, think of the work of Kapust and Witten and so on. So this has given powerful geometric tools to kind of study physics questions. And also, it's led to some non-trivial physics-inspired tools to study the geometry of the Hitchin system. One of these sort of major sources of interaction has actually been the study of the so-called 4D n equal to 2 classes theories. So this source of interaction is slightly different from the Kapust and Witten story, although there's a sort of relationship between them. If you are happy to work with the 6-dimensional picture, then there's a sort of dimensional reduction, different choices of dimensional reduction gives you either the Kapust and Witten picture or the classes picture. But for today's talk, I'll only be focusing on the story coming from classes theories. So the major underlying connection between classes theories and the Hitchin system is the fact that the Coulomb-Brown geometry of these n equal to 2 theories is encoded in the Hitchin system. So this has been an extremely active interface between physics and math. You can think of several ideas. I've listed a few here, things like spectral networks, the AGT conjecture, work of Nekrasov, Stratashvili, and so on. This has led to a lot of active sort of work in both directions, from physics to math and also from math to physics. So in all of these cases, the dictionary between n equal to 2 theories and Hitchin systems plays an important role. So one of the pieces of this dictionary is the fact that when the underlying n equal to 2 theory is superconformal, then the Deligne-Mumford moduli space m bar gn associated to the UV curve, which is some Riemann surface of genus G and n punctures, CGN, that is identified with the space of marginal parameters of this SCFT. So you actually have not just one superconformal field theory, you actually have a family of superconformal field theories parameterized by points on M bar. And there's a beautiful geometric interpretation, which is that non-perturbative dualities of these theories correspond to moving to different boundaries in M bar. So you can go to different codimension 1 boundaries, and they all correspond to different weak coupling limits of these quantum theories. Now, given this dictionary, it's very natural to ask what actually happens to the Hitchin system when we vary some parameter tau, which is like a coordinate on M bar. So our sort of starting broad goal for this project was to build a dictionary, first of all, to build the right language for describing the Hitchin system in this limit, and then to build a dictionary between the physics and the behavior of the Hitchin system as a family of integrable systems over M bar. In today's talk, I'll describe how to do this for Hitchin systems of type A, tame Hitchin systems of type A. I'll tell you what tame means. I'll also explain some surprises that we found along the way. So here's a quick overview of my talk. I'll give a slightly longer sort of recollection of the dictionary between n equal to 2 theories and the Hitchin system. And then I'll talk about sort of the main part of my talk, which is how to describe the Hitchin system on a nodal curve. And then in the final section, I'll talk about the connection to the Deligne-Simpson problem. And yeah, needless to say, at any point, feel free to stop me for questions. So I'll start with some brief recollections of the Seiberg-Witten story from the early 1990s. So they found that 4D n equal to 2 theories were an attractive sort of intermediate point between non-supersymmetric theories, which would be n equal to 0, or highly supersymmetric theories like n equal to 4. In 4D n equal to 2, you have still some degree of control coming from extended supersymmetry, but you also have richer physical phenomena that can happen compared to, say, 4D n equal to 4. So Seiberg and Witten came up with a strategy to solve for the low energy effective field theory at a generic point of what's known as the Coulomb branch of a 4D n equal to 2 theory. So of the different moduli spaces of vacua that can occur in 4D n equal to 2, sort of two distinguished cases are what are called the Coulomb branch and the Higgs branch. So Seiberg and Witten were working with one of these, where in the generic point, the infrared theory is an abelian interacting theory. So they basically noted that the low energy effective field theory is encoded in some nice geometrical way. And that is constrained by the electromagnetic duality of the infrared abelian theory and constraints coming from extended supersymmetry. So to put this in concise terms, you can basically say that this low energy effective field theory is encoded in what's called a complex integrable system. And the base of this integrable system carries a special Kähler metric, and that's identified with the Coulomb branch of the 4D theory. And the total space of the integrable system, which is actually a hyperkähler, that can be identified with the Coulomb branch of uh, the theory compactified on R3 times S1, where you sort of take the radius of this S1 to be very small. So it's very close to being a 3D theory, but it's like slightly away from it. So there's a subtle difference between completely dimensionally reducing and sort of continuing to work with the compactified theory. Now, typically, the fibers of the Seiberg-Witten integrable systems, they turn out to be either Jacobians or prim varieties of some Riemann surface sigma, where sigma is the Seiberg-Witten curve. So these are classical objects in algebraic geometry. Somehow magically they appear in this purely physics question. The lattice of the IR electromagnetic charges, gamma, is identified with H1 of the sigma b. And there's a symplectic pairing on sigma that arises from the analog of the Dirac quantization conditions, which we want to write it for dyons instead of just electrically charged and magnetically charged objects, purely electrical monopoles or magnetic monopoles. So that in the generalization is called the Dirac-Schwinger-Zwanziger condition. Now, once you choose a splitting of this lattice gamma into electric charges and magnetic charges, that corresponds mathematically to giving a principal polarization for the fibers FB, where the sort of IR coupling constant matrix is identified with the period matrix. These are again standard objects in algebraic geometry. And the n equal to 2 central charge function is given in terms of certain period integrals of a meromorphic one form that's usually called the Seiberg-Witten one form. So you pick some A cycles or B cycles, and then if once you pick this basis, there's a corresponding identification with the central charge functions. Okay, so far I've just recalled general information about 4D n equal to 2 theories. A particular large class of 4D n equal to 2 theories can be obtained by formulating the so-called 6D02 superconformal field theory. So there's one such theory for every simply laced Lie algebra. I will call that J. So you pick a Lie algebra, and then you compactify the corresponding theory on R4 times CGN. You have to take care to maintain some supersymmetry, so I have to do some partial twist. So in this process, I also insert some defect operators of the original 6D theory at some punctures on this Riemann surface. If you do this, then you get some 4D n equal to 2 theory, and this goes back to the work of Gatto and Gatto-Moore and Neitzke. So it's precisely in this sort of setup where you have this identification between the space of marginal parameters of these 4D n equal to 2 theories. These are the ones that are called class S theories, and the moduli space of complex structures associated to this Riemann surface, which I will denote by M bar. Now, the Seiberg-Witten integrable system associated to such a theory is basically identified with a particular instance of the Hitchin integrable system associated to the Riemann surface C of type J. Now, without punctures, so it's just some Riemann surface of, say, a high enough genus, uh, the following is the description of the Hitchin system. It's a complex integrable system whose total space is the moduli space of pairs V, phi, where V is a principal J bundle, and phi is a section of add V times K, where K is the canonical bundle. Now, strictly speaking, I should also impose a stability condition here, but let me not get into the details. But if you sort of know about this technical aspect, so let's just assume that I've already imposed this stability condition. I will have a little bit more to say about this towards the end of my talk. So now from this total space MH, consider the map where I just map to affine space B, where B is just the direct sum of some graded pieces, where each piece is just sections of some powers of the canonical bundle. I hope the notation here is not confusing. Capital K is the canonical bundle, while small k runs through the degrees of invariant polynomials of J. Say, for example, if it's SLN, my small k would run from 2 through capital N. So Hitchin showed that this map mu is a Lagrangian fibration, and that the generic fibers of the map are Lagrangian tori. So in keeping with our previous picture, the base of the Hitchin system parameterizes the Coulomb branch of the 4D theory, and the total space, which is hyperkähler, parameterizes the Higgs branch of the theory on R3 times S1. And the Seiberg-Witten curve is nothing but the spectral curve associated to the Hitchin system. You get the spectral curve basically by taking the characteristic polynomial of the Higgs field and setting it to 0. And the Seiberg-Witten differential is the canonical one form on the cotangent bundle of C, which I've written here as lambda dz, restricted to the spectral curve. So that's the story without punctures. Now, I want to allow punctures. I'm going to allow only particular types of punctures. These correspond to what are called tame defects. Mathematically, it corresponds to the restriction that I only allow cases where the Higgs one form has a simple pole at these punctures. You can relax this, and there's definitely a physics story corresponding to wild defects as well, but I will not be doing that in my talk.
Can I make some comment?
Yes, please. Yeah.
Can you go back one slide?
Yes.
Yeah, here you mentioned the Coulomb branch of R cross R3 cross S1 is the Hitchin modular space.
Uh-huh.
I mean, roughly speaking, this is true, but strictly speaking, it seems this is not the case. Some like a Coulomb branch is some quotient of Hitchin modular space.
Mm-hmm.
Depending on because of this you talk about this simplex pairing of line operator, right?
Yeah. Yeah.
And then some if you look at this Hitchin modular space itself do not satisfy this the quantization condition fiber.
Okay.
And then it seems like you need some quotient to satisfy this quantization condition for line operator.
Okay.
Anyway, so seems like a strictly speaking Coulomb branch of the this 4D n equal to 4 on R3 cross S1 is some quotient, a fiber-wise quotient of the Hitchin modular space. Anyway, so that's a bit subtlety, but it's not sorted out completely. But anyway, that's a comment.
Okay, good. Thank you. Thank you for the comment. So we'll sort of work assuming that we can sort that out if we wanted to, but yeah. Okay, good. So I will only allow tame defects for the purposes of my talk. So how does the integrable system look when we allow these tame defects? So you can sort of copy our previous definition of the Hitchin system, but everywhere I had the canonical bundle, I'm going to replace it by the canonical bundle twisted by some divisor D, where the divisor D is just the sum of the points corresponding to the location of the punctures. So basically, I have again a moduli space of pairs v comma phi, where phi is now a section of add v times k of d. And the Hitchin base is again a direct sum of some graded pieces, which are again sections of powers of k of d. So one difference here is if you sort of mimic the old definition, what you get is not a symplectic integrable system, but a Poisson integrable system. And that is for a very simple reason. This is because dimension of B, as calculated from this formula here, will turn out to be greater than just half the dimension of the total space. These additional base parameters, these are sometimes called Casimir parameters in the math literature, they correspond to the freedom that we have in varying the residues at each of these points in the divisor in some fixed sheet of the Lie algebra. So sheets are a sort of nice way to stratify any complex Lie algebra. So think of the adjoint or coadjoint orbits in the Lie algebra. Think of all orbits of some fixed dimension. That is going to be some complicated variety. Think of the irreducible components of that variety. That's called a sheet. So now go to each puncture on the Riemann surface. If you vary your residue in some fixed sheet, what you will be doing is you will not be, say, changing the pattern of multiplicities of eigenvalues and so on. Say your residue is semi-simple. If you have some multiplicity structure, you will not be changing the multiplicity structure, but you'll only be changing the actual eigenvalues. So you are in principle changing the adjoint orbit, but you're doing it in some controlled way. So doing these kinds of changes correspond to these additional base parameters. In physics terms, they correspond to turning on local mass deformations at these punctures. So we studied this in an earlier work with Jacques Distler, but I'm not going to talk about these for today's talk. In fact, what I will go ahead and do is I will fix these residues to actually be nilpotent at each of the punctures. The moment you fix the residues, you get a symplectic integrable system. And the one you get by making all these nilpotent is the one corresponding to a superconformal field theory. Basically, I'm setting all the masses to 0. Now, depending on these nilpotent residues, my base B is going to be modified. It's not just going to be sections of either K or K of D, but it's going to be sections of some other line bundles L of K. So both in my talk and in our paper, these line bundles LK play an important role. They're sort of everywhere dense in our paper. So here's what these line bundles are. They sort of look like the original definition, basically K of D to the powers to raise to the powers of these small k's, but they're additionally tensored with some uh, copies of these EIs multiplied by some 0 orders chi k's. So what they basically encode is the moment you have these nilpotent residues, if those nilpotent residues are not regular, these chi's are going to be non-zero. So if you look at the coefficients of the characteristic polynomial of the Higgs field, they are now going to have slightly modified pole orders. So I've just encoded the change in pole orders in terms of these numbers chi k. I'll give a few examples later on. So whenever I refer to the tame Hitchin integrable system, I will always talk about the symplectic integrable system that you obtain by doing this procedure here. Any questions?
When you say, I mean, ta target is hyperkähler, but how to say, which symplectic form do you use? I presume.
Okay, great. So throughout my talk and in our paper, we only work with the complex structure I. Sorry, there's an aircraft flying near me. I don't know if that's interrupting.
I mean, standard notation Hitchin system, Hitchin modular space. Right? I is holomorphic. I mean, Hitchin fiber is holomorphic in complex structure I.
Yes, that's the complex structure I'm using. Yeah.
Okay. But the symplectic form is omega k. Because when you say Lagrangian,
omega, it would be the complex symplectic form that's usually called omega I.
Capital omega I. Okay, thank you.
Omega I.
Okay, yeah. Thank you. So you just look at the holomorphic symplectic form.
Yes.
Okay, thanks.
Yes. Yeah. Yeah, so all of these things come in P1 family. So you can ask similar questions in other complex structures as well. Okay, so this is the definition of chi-k, but I'll now give you a simple algorithm that allows you to compute these. So first recall that nilpotent conjugacy classes in SLN are classified by partitions of n. So let pi be the partition label corresponding to a particular nilpotent conjugacy class. Now we can represent this as a Young tableau by using its parts as column sizes. So I'm just going to, so the algorithm to compute chi is basically the following. You take the first column of the Young tableau and fill it with ones, and you take the second column and fill it with twos and so on. Write all the numbers you have in the Young diagram column-wise, while dropping the leading one. The string of integers that you get by doing this operation is basically going to be the zero orders chi-k. So here's an example. So think of the nilpotent conjugacy class corresponding to 431 in SL8. We can represent it by the following Young diagram. So I follow the algorithm, fill the first column with one, second column with twos, and the third column with threes. So I list this set of integers in non-decreasing order while dropping the leading one. So I'm dropping the leading one here because we are working with SLN and not GLN. If you did things for GLN, you can keep this one. So this is the combinatorial way in which you calculate chi-k. So you can see here that you don't get arbitrary sequences of integers. So if you think of which sequences lie in the image of this map chi, there's some conditions. For example, if there's a certain number of threes, that should be less than or equal to the number of twos, because there's an ordering to the sizes in these Young tableau. I'm going to always pick them to be non-decreasing. There's a corresponding condition on these sequences. This will be important a little later in my talk. Okay, so now I have this tame Hitchin integrable system motivated by some physics considerations going back to work of Gato Razamat, which is kind of also a follow-up to earlier work of Gato and Witten. We introduce the following definitions for any tame Hitchin integrable system. We call a Hitchin system to be a bad one if any of these line bundles LK that I defined in my previous slide, if any of these line bundles actually have a H1 for any value of K. We call a Hitchin system to be ugly if they're not bad, but they have a non-trivial kernel for this map kappa from local mass deformations to global mass deformations. So I won't try to be very precise about this here, but in terms of physics, what this means is this indicates the presence of some free hypermultiplets in the corresponding n equal to 2 theory. And there's a difference between the local and global Poisson deformation spaces. Now, the third case, namely that of a good Hitchin system, is basically defined to be one that's neither bad nor ugly. Now, it turns out we actually don't have to always carry around this trifecta. There's a simpler classification, which is just a dichotomy. And that basically involves keeping track of whether your Hitchin system is bad or it's not. So instead of having to say not bad at various points in the paper, we thought we'll just give it a simpler name. So we just call those okay Hitchin systems. So in our paper, you will basically see this difference between okay and bad. It ends up playing an important role. It also turns out this okay condition, it turns out to be a kind of stability condition. I'll talk about this in the third part of my talk.
I have a question. What does it mean, this bad Hitchin system, in terms of physics?
Okay, great. So it basically means that you have to be careful when you take the IR limit. So the origin of this good, bad, ugly goes back to this work of Gatto and Witten in 3D n equal to 4 theories.
Yeah.
So there they observed that so it's not always true that the UV R symmetry that's visible, say, in a Lagrangian, is the same as the IR R symmetry. Whenever these two differ, you can have sort of your ability to predict what the IR limit is sort of constrained. And the way to detect this is you look at R charges of some monopole operators. When they don't lie in the usual ranges, that's a way to detect these bad 3D n equal to 4 theories. And there's a corresponding statement for 4D n equal to 2. So in fact, the Gayato-Razamat condition is basically a condition on the Higgs branch of these 4D n equal to 2 theories that basically mimics this Gayato-Witten condition on the R charges of monopole operators.
I see.
That's the origin of this condition.
I see.
But we sort of gave a purely Hitchin system version of these conditions.
I see. Okay, thanks.
Okay, great. But yeah, thanks for that question. Okay, so now I'm going to take all of this. So all of this was like introduction to our core subject. So I'm going to take this entire structure and try to degenerate this to a nodal curve. This here is a tame Hitchin integrable system. Okay, so here is the physics motivation for doing something like this. So if you go to any codimension 1 boundary in M bar, you basically go from smooth C to some singular C. This limit corresponds to the appearance of a weakly coupled vector multiplet in the physics setup for some gauge group, which I will call H, together with some matter content, which could either be conventional matter in the sense of hypermultiplets, or it could be exotic superconformal field theories and so on. But the point here is the strict nodal limit corresponds to the limit where G squared Yang-Mills for this gauge group H becomes 0, which is the same as saying this imaginary part of the complex coupling is going to infinity. Now, if I normalize this nodal curve, I would get some smooth curve, which is different C tilde. It has a new genus G tilde. And there's now going to be another different superconformal field theory associated to this C tilde. So this is the operation in one direction. You can also think about the operation in another direction. Basically, you start with this SCFT corresponding to C tilde, which could actually be disconnected. So it could actually be some bunch of components. And you're given a rule for gauging the global symmetries associated to this superconformal field theory at some of these punctures. And there's a rule for how you sort of jointly gauge global symmetries associated to two different punctures. And you couple these global symmetries using this vector multiplet. So then you again get back to this description in terms of vector multiplet coupled with some matter theory. And then you move further into the moduli space, and then you get a SCFT corresponding to the original Riemann surface C. Now, these different groups that you see, well, any of these groups H, they typically, they turn out to be subgroups of SUN. And the interesting fact is that you get different groups HI at different boundaries of M bar. This is a striking fact. It's a generalization of a feature that was originally observed by Argyris and Seiberg. So you might want to call this generalized Argyris-Seiberg duality. So our point of view is that we want to develop the mathematical story underlying this object at the center. And we want to do this in a way where this theory on the nodal curve, or the Hitchin system on the nodal curve, sort of knows everything about what's on the left and what's on the right. So it acts as a mediator between the two theories on C and C tilde. Okay, so I should point out that this question has been studied in the physics literature, and rules that govern the relationship between the SCFTs on the two smooth curves, C and C tilde, are known thanks to Gato, Shackleton, Distler, and Gato, Moore, and Tachikawa. What we want to do is derive these rules from a nodal Hitchin system. So here is a quick recollection of some background mathematical literature. The study of bundles on nodal curves has a very long history. This can be thought of as a higher rank non-abelian version of the study of the Jacobians on a nodal curve. The study of Higgs bundles, however, is a lot more recent. There are a few papers in the mathematical literature from the last 4 or 5 years. There's also some pioneering work by Nekrasov and Shervov Televev from the point of view of integrable systems that goes back maybe 15 to 20 years. The goals in these above works were somewhat different from ours. So for our purposes, we basically had to develop the story from the basics. So, and I'll try to tell you how that works. Okay, so basically, we want some sort of analog of the canonical bundle. Luckily for nodal curves, there's a natural analog. On a nodal curve with some node at point P, there's a natural analog of the canonical bundle that's usually called the dualizing sheaf. I'll denote it by omega. This sheaf is defined as the push forward of the sheaf of meromorphic differentials with at most simple poles at the inverse image of the point P, where P is the node, and the map nu is basically the normalization map. So basically, you think of a node, and then the pre-image of the node under the normalization is going to be 2 points, and you impose the condition that these space of meromorphic differentials have only simple poles at the 2 pre-images. And there's also a condition on the residues which says that the residues should be equal and opposite in sign. So you take meromorphic differentials obeying this condition and you push them forward under the normalization map. That gives you this dualizing sheaf. So we're going to use this in place of the canonical bundle and mimic everything from before. Most things go through, except for the following important point. The Hitchin map in the sort of quote unquote integrable system that you get in this way is actually not proper when the base curve is nodal. Some of the Hitchin fibers could actually be non-compact. So loosely speaking, to get an honest integrable system, we want to sort of quotient out these fibers. You could do something more interesting, which is try to actually compactify them, but that's not what I'll try to do today. So let's try to do this sort of loosely defined quotienting out procedure, and we get a smaller moduli space, which is a Poisson integrable system. So the fiber directions that were originally non-compact, they have natural symplectic duals on the on the Hitchin base. So those pieces of the Hitchin base that are symplectic dual to these non-compact directions, those are the ones that we call center parameters.
I have a question.
Yeah.
So I cannot imagine that sorry, maybe I just don't have imagination, but I cannot see how does this Hitchin fiber becomes non-compact when you go to nodal curve. In which point does it become non-compact?
In the strict nodal limit. So
okay.
If you want to think about this in terms of physics, so you write, say, the metric on the Hitchin system. So there's going to be different things that sort of scale the fiber directions. For example, if you write the metric in terms of the radius of the circle S1 in the compactification, there's going to be a factor of that and so on. But let's keep all of those fixed. You just send G squared Yang-Mills corresponding to this gauge group H to 0. Under that limit, you will see that the metric on the fiber directions is getting scaled.
I see.
And in the strict limit where G squared Yang-Mills, some of these directions become non-compact.
Okay, can you identify which point on the Hitchin base does the fiber become non-compact? Can you tell?
No, so they, in the nodal limit, some of these fibers become non-compact everywhere on the Hitchin base. But what I'm saying is there's a sort of natural pairing between the fiber coordinates and the base coordinates. So say you had a 10-dimensional Hitchin system and 4 of the fiber directions are compact. You can find a corresponding 4-dimensional subspace in the space of the base parameters. That is in the center parameters. They will play an important role in the story.
Okay, I see. Okay, thanks.
Okay, in fixed setup, these will become related to the webs corresponding to the scalars in the vector multiplet of H. Was that helpful?
Yes, yes.
Okay. So rational of Darboux coordinates on base and fibers such that the symplectic form is du wedge d theta, and theta are the coordinates for the fiber directions that are becoming non-compact. Then their corresponding symplectics, which denote in the UI, they are the coordinates on the space of center parameters. You can go ahead and further set the center parameters to specific values, or you can even set them to 0. In that case, you would again get eclectic integrable. These center parameters sort of behave like mass parameters, but really in the physics picture, they are webs of the scalars in the vector multiplet. Nodes separating or non-separating. For this whole story, it turns out separating nodes are more interesting. So let me just talk about those. So let's say you have a separating node in which my Riemann surface factorizes into two Riemann surfaces of smaller genera. So let's try to understand what happens to the Hitchin system. If I had these line bundles LK, using those line bundles LK, I'm going to find the, you basically take the original NK and you tensor it with the structure sheaf of CL or C right. These are the two components of my separating node. The other two sheaves are closely related to the above, but they have an additional tensoring with O of minus P, where P is the actual node. I will call these the kernel line bundles because they naturally arise as kernels of the restriction maps either to the left component or the right component. So there's a left kernel and the right kernel. So here's the algebraic geometric interpretation of what's a center parameter. On my previous slide, I gave a symplectic geometric interpretation of those. So whenever you have a non-zero section for both the restriction bundles, then there's a unique way to glue them together. This is the data that's encoded in the value of the center parameter at degree k. You can also think of this as the degree k piece of the image under mu of the residue of phi on the pre-image of the point P. Okay, so now let bk be the graded dimension of the space of center parameters, so the bkc. By construction, you can see that this is either 0 or 1. But we want to understand what are these sort of global conditions, like these are some conditions for every value of k. I want to understand, first of all, what's allowed at each value of k. I then also want to put together how it looks for different values of k. So to this end, let's also define some smaller Hitchin bases. I'll define B left to be the sections of the kernel on the left, and B right to be sections of the kernel on the right. These vector spaces will end up being bases of the left and right integrable systems. And BKL and BKR are their corresponding graded dimensions. So we want to understand what are basically the different kinds of separating nodes that can arise. So this is an interesting now algebraic geometric problem. You can actually solve this. So there's a large class of nodes, which are called standard nodes, in which H1 for these kernel line bundles are 0. And correspondingly, the center parameters are one-dimensional for each value of k. Any such node is what we call a center, or is called a standard node. There's a second more interesting case where some of these kernel line bundles start having H1s. So notice here there's an AND and OR. So it could happen that both LKL and LKR have H1s, or it could be that only one of them has a H1. This can happen for any value of k. The moment that happens, I'm going to have what's called a restricted node. And corresponding to that, I'll have a vanishing center parameter for that value of k. That's kind of the indication that there's some kind of restriction happening. There's a third interesting case, which is kind of a stronger version of the second case here, where I don't just have H1s for the kernel line bundles, but I actually have H1s for the restriction line bundles. So I've recalled for you the definitions of these. The restriction line bundles have a higher degree. So asking for H1 for that is a slightly stronger condition. Whenever this is true, the second condition here, the condition for the restricted node in bullet point 2 will also be obeyed. But you have some new phenomenon here, which is that if you compute H0 and H1 of these LKs, and you take the limit from the smooth curve to the nodal curve, they both increase while still keeping h naught and h naught minus h1 constant. This is of course true in the first two cases, but they were true in a kind of trivial way. H naught and h1 themselves were constant, and consequently h naught minus h1 was also constant. But in this third case, they're getting more interesting. H naught and h1 jump, but they jump in a way that h naught minus h1 remains constant. So we'll just give this a different name. We'll call these non-regular restricted nodes. You will see why we have this name. So what happens in these non-regular restricted nodes is that if you sort of naively copy your earlier definition of the Hitchin system, you get a base that's too big. So in these cases, it turns out, say, BKL and BKC are 0. I've just made a choice here. I've just taken the H1s to occur on the left. Unlike the bullet point 2 here, in bullet point 3, these H1s for the restriction line bundles, they occur either on the left or on the right. You never have a case where this happens on both sides. And this is related to the fact that we always work with okay Hitchin systems. This is not obvious from what I'm presenting here, but this turns out to be true. So what happens is if you naively copy your definition of the Hitchin basis, you get something that's too big. In particular, you don't get a flat limit of the family of Hitchin integrable systems. You start from something on the smooth curve, but then suddenly if you go to the nodal limit, you have some Hitchin system that has a bigger dimension. So that's clearly not what we want. That's not natural from the physics perspective. Luckily, there's a natural and unique fix. You basically take the original definition of the Hitchin base on the right, you modify these LKRs by some tensoring with some O of minus nk times p, where nk is basically given by the value of h1 on the left for the kernel on the left. So this turns out to uniquely fix our dimension problem. Moreover, let's define this quantity chi k node. This is a new set of vanishing orders that we have at the node, which is just 1 plus nk. So if all these nks were 0, all these chi k's would just be 1. That basically corresponds to the case where the nilpotent at the node, which is kind of like a defect that you are now inserting at the normalization or the two images of the node in the normalization, that is just the regular nilpotent. Whenever nk is non-zero, then this is going to change. That's the reason we call these regular restricted nodes and non-regular restricted nodes. So for now, let's just take this as a definition. We have these interesting chi k's that are deviating from 1 whenever this h naught of lk jumps. So all of this is at each value of k. We now want to understand how this looks when we put this together for different values of k. So we have a neat theorem that governs how this looks. So it turns out these vanishing orders chi k node that I defined in the previous slide, they uniquely determine a nilpotent orbit O. Basically, to do this, I have to use the algorithm that I alluded to earlier, but I have to now use it in the inverse direction. I have to use the converse of that. Uh, and it turns out not every nilpotent orbit O actually occurs as a nilpotent, as a nodal nilpotent. There's actually some restrictions on those. Furthermore, the resulting values, non-zero values of these graded dimensions of the center parameters are such that they can be interpreted as invariant polynomials for some particular subgroups of SUN. You don't get arbitrary subgroups, you only get subgroups of type SUK or SPK. And there is part C, which is a kind of joint constraint on the nilpotent orbit O and the different ranks that can occur for these H's. So this might not seem very obvious, but you get this constraint naturally from studying the nodal limit. Notice that asking that this left-hand side here, P1 minus 2, should be less than the right-hand side here, which is 2 P1 minus P2 minus 1, that turns out to impose some conditions on the nodal nilpotent itself. So this gives a pair O comma H. This theorem gives a pair O comma H to any node in the Hitchin system. So in this sort of notation, the standard node basically corresponds to the pair n comma sun, where this is the partition n corresponding to the regular nilpotent. non-separating nodes turn out to always be standard. That's why I've sort of been talking about separating nodes in my talk.
Sorry,
Okay, so
sorry,
what's the
my
physical
algebra.
interpretation of all of
Can
these
I ask a
things?
question?
Yeah,
So this
yeah, please go ahead. Yeah.
my algebraic geometry background is too weak, but so this theorem is stating that how this nodal limit will give you consistent Hitchin moduli space.
Yes, a flat limit of the Hitchin system.
Okay. So you have like a three region, right? One is the gauge coupling non-zero and the non-zero and the smooth spectral curve is sorry, the curve is smooth, and then
Mm-hmm.
in the middle you have the gauge coupling goes to zero, and which is the boundary of
Right,
the Teichmüller space and so on, or
right,
moduli space of curve. Um,
right,
then you get the nodal curve, and on the right you have like a decoupling limit, right? So there are two theory
right,
that glue
right.
decouple two theory. And this theorem will tell
Exactly.
us that so from left to right, you can just smoothly this theorem interplay from left to right, you mean? Is it?
Yes, and it tells you what
Yeah,
kinds of things occur in the center.
in the center. Okay, okay. And so
Yes.
if you go to the right, you have a two decoupled Hitchin moduli space to disjoint, I would say.
Yes.
Okay. And then
In
in
the
the
case
mid,
of separating nodes, yes. Yeah.
I see, I see. Okay, thank you.
You can do all of this for non-separating nodes as well, to be standard. That's sort of why I focused on the non-separate, so separating nodes as an example, but the theorem holds for non-separating nodes as well.
Okay, thanks.
Okay. So let me quickly tell you what the physics interpretation of this is. The nodal nilpotent O should be thought of as labeling the defect obtained by taking the OPE of all the defects on C left. So I've just made a choice that the restriction on the node, say, comes from C left. So if it has some number of defects, you sort of successively take OPE of those. At each point, you bubble out, say, two of the defects and replace it by the right-hand side of the OPE. If you do that for all the defects on C left, you will be left with just C right together with the resulting defect from doing OPE for all the defects. And that defect is the one labeled by this nodal nilpotent O. And part C constrains the kind of defects that you get by such OPEs. And the different H's that we have here in part B are basically the different weakly coupled gauge groups that can appear in class S theories of type A. Okay, so actually, how am I doing on time?
We're flexible at time, so if you want to take more time, you can go ahead.
Okay, so then maybe
Yeah.
I'll just quickly show an example. So all
Okay.
of the present discussion has been like very general, and maybe it was too complicated. So
Uh-huh.
let me pick a Hitchin system corresponding to a four-punctured sphere in SL4. I will take the residues to lie in the following orbits. Two regular nilpotent residues corresponding to the partitions 4 and 4, and two minimal nilpotent residues corresponding to the partitions 2 and squared and 2 and squared. I now follow my algorithm with the Young tableau. I compute the corresponding zero orders chi k's. They have the following form. Basically, whenever you have something regular nilpotent, all the chi's are just one. And the extreme case of a minimal nilpotent, which is the smallest non-zero nilpotent orbit, basically it's the smallest non-trivial defect you can have, that always has zero orders of the form 1, 2, 3, 4, all the way up to n minus 1. So those are the only ones I have here. Now we know that M04 bar has three boundary points corresponding to the three different degenerations of a four-punctured sphere. In two of these degenerations, uh, it's going to look in the following way. Basically, I have one copy of the regular defect and one copy of the minimal defect on both sides of the node. These limits correspond to the gauge theory that's basically a SU4 gauge theory with NF equal to 8. There's, of course, two different SU4 gauge theories here. They're not the same, but they sort of have similar properties. In both of these cases, the node that I get is actually the standard node. This is a calculation that you can do using all of these tools that I've built for you. There's a more interesting case, which is the other boundary in M04 bar. That corresponds to taking two of these minimal defects on one side and leaving the two regular ones on the other side. In this case, you actually get a SU2 gauge theory that's coupled to some non-trivial superconformal field theory corresponding to this fixture on the right-hand side. That's called, it's given some name R4. The name does not matter. But the point is you get something which is just a SU2 theory as opposed to a SU4 theory for the other two limits. And you also get some hypermultiplets in the fundamental representation of SU2. Now, this is an example of a non-regular restricted node. In this case, in fact, you can compute the nilpotent, and it turns out to be the subregular nilpotent in SL4. And so the pair that we would assign to this restricted node is 3, 1, which is the partition label corresponding to the subregular nilpotent orbit, and the group SU2, which corresponds to the gauge group that we get in this weak coupling limit. Is this example clear? Great.
Yes, yes.
Yeah, thank you. So, okay, so here are a few comments. So what is it that we learned that is new from the theorem? So I should mention that each part of the theorem was in some sense expected from the physics picture, but it's reassuring that we could give rigorous mathematical proofs using our definition of the Hitchin system. Furthermore, I would argue that part A of the theorem places the notion of what it means to do OPE of codimension 2 defects of the 6D theory on slightly stronger mathematical footing. There's also a technical point here. Part C is slightly stronger than what was previously known in the physics literature as an a priori result. But let me sort of not dwell on that too much. But purely mathematically, like if you're a mathematician studying the Hitchin system, I would argue that each element of the theorem that we proved is quite surprising. For example, the integers that I called chi-k node, the fact that they uniquely determine a nilpotent orbit is already quite surprising. So the way I defined chi-k node, it had no a priori reason to sort of fall under the image of my original Young tableau algorithm. So I gave you an algorithm to calculate these zero orders. If you just randomly studied some nodal limit of a Hitchin system, maybe you would have gotten some string of numbers for chi-k node that's not in the image of that algorithm. But surprisingly, that never happens. These chi-k node, they always end up determining a unique nilpotent orbit. Furthermore, why this particular list of O, H? So you are some mathematician studying the SLN Hitchin system. Why should you now suddenly find particular subgroups of SUN that are of type SUK for some smaller k, or just SPK occurring in this weak coupling limit? That's not a priori clear. There's of course a physics explanation, but I think there is still some interesting geometrical questions in mathematics as to why we get only this list of O's and this list of K's. Oh, sorry, H's.
Could you remind me what is the part A and part C?
Oh yeah, sure, sorry. So part A is the statement that chi-k node uniquely determines a nilpotent orbit at the node.
Oh, I see.
And part B is a restriction on the different H's that occur. Well, actually, it's a restriction on the center parameters. Part C is a joint restriction on the different H's and the different O's that can occur.
Oh, I see. Okay, thanks.
Okay. So yeah, I would argue each of these statements is surprising from a mathematical point of view. So you can, for example, take these statements and ask, are there analogous things that you can say for non-type A Hitchin systems? At least in the simply laced cases, physics has some predictions, but it remains to sort of build the corresponding rigorous mathematical framework. We did not do that in our paper, and it's something we are thinking about. Okay, I'll pause here for questions.
I have a physics question. I mean, if you go to nodal limit or like like pinch some cycle, whatever.
Yeah,
Is any like a reason this coordination two defect arises? Like it's an intersection in five ranks, right?
correct. Yeah,
Is any some physical like argument or
that's a good question. So
yeah, the pinching will arise some intersection in five rank.
you could maybe argue that it has to be like there is this sort of conjectural picture of what it means to do OPE of codimension 2 defects.
Mm-hmm.
So you could maybe argue that there should be some codimension 2 defect on the right hand side of uh, the OPE of all the defects on say C left. But what's not obvious is that that would also be a tame defect, for example.
Mm-hmm.
Like, why should OPE of tame defects be closed? Maybe there's some weird choices for which you get something wild. So I don't know first principles derivation of this fact. I only know different consistency checks for the claim that if you at least work with the defects that I'm working with, like these particular tame defects,
Mm-hmm.
their OPE is actually closed, and uh, the resulting defects actually they look like basically the ones that are allowed by Part C here.
I see. Okay. Uh-huh.
I only know consistency checks of that statement.
Okay. Uh-huh.
I don't know a first principles proof of that.
Okay. Thanks.
Okay, great. So that sort of is the end of the nodal curves part of my talk. Now I'll talk about a surprising application that we found to what's called the Deligne-Simpson problem. So let me just start by recalling what the Deligne-Simpson problem is. It's actually a classic problem in linear algebra that goes back to actually work of Riemann, Hilbert, and so on. But it was given a sort of nice formulation that extends to, say, arbitrary groups by Deligne and Simpson. So I'll just state the problem for SLN. So the problem basically asks you to identify necessary and sufficient conditions on some list of conjugacy classes C1, C2 till some number C p plus 1 in SLN, such that I can find representatives in these conjugacy classes, which I'm calling MI, uh, that obey the condition that the product of all of these should be the identity matrix. Now, this is a matrix equation, but what I really want is conditions on conjugacy classes. I want to emphasize this. I don't want just conditions on individual matrices. This is actually the multiplicative version of the Deligne-Simpson problem. There's also a corresponding additive version, which is basically a similar question in the Lie algebra. Replace these conjugacy classes by their corresponding objects in the Lie algebra, and then you replace this product by a sum. Now, there's an interesting interpretation of the Lie group version of this problem. It's basically equivalent to asking for the non-emptiness of what's called the irreducible character variety on P1. That's basically the moduli space of irreducible representations of the fundamental group. Um, there should actually be a pi1 here. This is not just C0P1, it's actually pi1 of C0P1 into the complex group SLN. So it's a little exercise to check that the only non-trivial relation among the different generators of the pi1 of some punctured sphere is basically a relation of this form. So you have monodromies around, say, each of the punctures, and the only condition is that the product of all of them should be the identity. So through the Riemann-Hilbert correspondence and the non-abelian Hodge correspondence, this problem, the Deligne-Simpson problem, is actually related to the non-emptiness of the moduli space of semi-stable Higgs bundles. So this is the kind of relationship you have. On the extreme right-hand side, you have the moduli space of local systems, which is sort of the natural home for the Deligne-Simpson problem. You can use the Riemann-Hilbert map or the holonomy map to go from that to the moduli space of flat complex connections. And from this middle box, you can use non-abelian Hodge in both directions to go to the moduli space of Higgs bundles. So here, for this thing to work, I should insert again some stability conditions, and basically imposing the stability stability conditions on the Higgs bundle moduli space turns out to be equal to asking for the existence of a solution to the Deligne-Simpson problem on the extreme right-hand side. Okay, so let's actually focus on a particular case of this problem. So let's say the conjugacy classes on my third column, the local systems column, they're all semi-simple. And let's further impose the condition that one of the conjugacy classes, say C(p+1), is actually regular. Regular means is the largest possible, it has the smallest possible centralizer. In this case, Simpson actually solved the problem completely in a paper in 1992. So we'll call these cases the regular cases, and I'll recall his solution for you here. He basically gave two conditions. Taken together, they are necessary and sufficient for a solution to exist. And the first condition is basically conditioned on this number D, which is sort of the candidate number for the total dimension of the character variety. So whenever it's non-empty, this would be its dimension. So it's basically 2g minus 2 times dim_g plus the sum of the dimensions of each of these conjugacy classes. I should have indicated here that the sum runs through all the punctures, 1 through p+1. So the first condition basically says this capital D should be greater than or equal to 0. The second condition is in terms of certain multiplicity data. So let MA be the largest among the multiplicities of the eigenvalues in any representative in the conjugacy class Ci, and define this RA to be N minus MA. Sorry, I've confused my subscripts here. All these I's should just be A's. Yeah, so these should just be capital MAs. So these RAs are just capital N minus MIs. And Simpson's second condition says that if you sum over these RAs from 1 through P, the small n should actually be P. Basically, you leave out the regular conjugacy class. So the sum of the RAs from the rest of them should actually be greater than or equal to N. So the surprising result that we found is that recall, I gave these conditions for what it means for a Hitchin system to be okay or bad. So it turns out, if you take any of these moduli spaces of local systems, you transform them to some moduli space of Higgs bundles, and you ask when the corresponding Higgs bundle or Hitchin system is okay. It turns out in all of these cases, that's the same as asking for Simpson's conditions to hold simultaneously. So in other words, the okay condition for these particular Hitchin systems is the same as asking for a solution to the Deligne-Simpson problem. Now, the way we arrived at this result is a bit roundabout. That's why it was a surprise for us. We arrived at this result through the classification of restricted nodes. So you might ask, what does this have anything to do with the nodal curves problem? It turns out there's a surprising connection between the existence of a restricted node and the existence of bad Hitchin systems with at least one regular conjugacy class. And the connection is the following. So consider a node in which C left is just a P punctured Riemann surface, C0P, and CR is something generic. Now, using this data, I'm going to form a P+1 punctured Riemann surface, C0P+1, where the new puncture, at the new puncture, I insert a full defect, which basically means I give the Higgs field a regular residue, a regular nilpotent residue. It turns out, asking for the original node in C left intersects CR, they meet at the point P, asking for that node to be restricted is the same as asking for this new Hitchin system on this P+1 punctured sphere, asking for that to be bad. So this is not obvious, but this is something that follows from our framework naturally. And since our whole project was to sort of classify the allowed restricted nodes, as a corollary, we also had a classification of all bad Hitchin systems with at least one regular residue. And since bad is the opposite of okay, we also had a classification of all okay Hitchin systems with at least one regular residue. So this is kind of how we landed on the connection to the Deligne-Simpson problem. But you don't have to necessarily.
I have a question.
Yeah.
Is it stable? Is the Higgs bundle stable? This CR with.
So it is stable when the okay condition is obeyed.
Okay.
So
Even sphere with one puncture?
no, so that's taken care of by the OK condition. There's no way to satisfy the OK condition if you just take one puncture. You need at least 3 punctures.
Oh, okay, okay. I see, I see. Okay, thanks.
So it's not obvious, but if you play with the OK condition, you will see that that naturally comes out.
Okay, I see.
Okay. So in this picture, existence of a solution to the Deligne-Simpson problem on the extreme right-hand side is basically the same as asking for the existence of some semi-stable moduli of Higgs bundles on this extreme left-hand side. So that's the reason I said initially that the OK condition is some kind of stability condition. So yeah, so we arrived at this through the nodal curve story, but that may or may not be natural. So you can perfectly well pose an independent question. Basically, I introduced a dichotomy in the world of Higgs bundles between those that are okay and those that are bad. Is that just directly related to the existence and non-existence of solutions to the Deligne-Simpson problem? That's a perfectly well-defined question. You may not want to use the nodal curve story at all to study this. What we did show in our paper is that for these regular cases studied by Simpson, this connection is indeed present. And so it's an interesting reformulation of Simpson's work. We also have some strong evidence that this close relationship persists more generally. So in our paper, we conjectured as much. We basically gave 2 versions of our conjecture. The weaker version says the OK condition is just sufficient for the solution to the Deligne-Simpson problem to exist. The stronger version says that it's actually necessary and sufficient. Um, so there's some evidence that the sufficiency part is enough for whatever expectations you might have from physics. But actually, all the available evidence we have is compatible even with the stronger version of the conjecture. So that's actually why we went ahead and gave the stronger version as well. So there's some ongoing work where we're actually trying to prove at least particular instances of these conjectures. So they involve connections to lots of other fascinating questions. In the mathematical literature, for example, there's a special role played by things called rigid local systems. These are the ones where you don't have a moduli space, but you actually just have a single point. There's a unique solution to the Deligne-Simpson problem, if you wish. And there's important work of people like Nick Katz who have studied rigid local systems because they have some important arithmetic applications as well. But you can just think about them in the purely complex world. And it turns out these rigid local systems, they correspond to Hitchin systems that physicists would call are basically just free hypermultiplets. So free hypermultiplets means you have some Higgs branch, which is just, again, something very simple, which is just some copies of the quaternionic space, h to some dimension d. But the Coulomb branch is basically just a point because it's just hypermultiplets. I don't have any vector multiplets. That's actually why they're related to rigid local systems. There's also some interesting connections to representation theory of quivers and work of people like Coulomb and so on. But all of this is still ongoing work. The broad sort of claim I want to make is rethinking all of these connections in terms of this OK condition on these line bundles LK. It seems like a promising way to sort of rethink the Deligne-Simpson problem, both in, say, cases where it's well understood and maybe also in cases where it's not that well understood. For example, in the regular cases, the ones that we did show there's a direct connection, when the Hitchin system is bad, the nodal curves picture also gives you this pair O comma H corresponding to every bad Hitchin system with a regular residue. So from the traditional way of thinking about the Deligne-Simpson problem, you may not have thought of this pair O comma H at all. Like, why would you try to associate something like that? But it turns out there is some canonically associated pair of a nilpotent orbit and a subgroup of SUN associated to every instance where you fail to have a solution to the Deligne-Simpson problem. So you might want to ask the following question. So let's say you don't have irreducible representation of the fundamental group. but maybe you still have a reducible representation. So in other words, maybe you have a reducible local system on C0P1, and maybe this pair O comma H might help you identify that reducible local system. So this is again something one can hope to do. So there's a further sort of story that we did not develop in our paper, but you could basically take all of the questions that we were asking. Instead of posing these questions on the Coulomb branch side, you could also imagine posing the same questions on the Higgs branch side. So basically take a class S theory, go to the limit where you have a weakly coupled gauge group, what's happening to the Higgs branch? So this is a highly non-trivial problem, and there were conjectures put forward by Gayato, Moore, and Tachikawa as to how the hyperkähler uh, Higgs branches should obey under these limits. It basically says that the smaller groups H, you should interpret them as hyperkähler isometries of some, again, bad theories on either C left and C right. Nakajima has studied the GMT conjecture in several cases, and I believe our results are compatible with his results, but I think the Higgs branches are a lot more complicated objects. I think that's an interesting direction for future work. You could, for example, ask if you can arrive at the kind of classification of H and O purely from a Higgs branch calculation. I think that would be fascinating. Okay, so I'll end with some further applications. So basically what our work gives is some kind of dictionary between the nodal Hitchin system and Coulomb branches of n equal to 2 theories. One can imagine using lots of other classes tools to probe the nodal Hitchin geometry further. For example, spectral networks, different supersymmetric indices, partition functions, and so on. Uh, you can, for example, try and understand this body of work on what are called higher Fenchel-Nielsen coordinates. There are particular Darboux coordinates on either the moduli space of flat connections or the character variety that are again adapted to different choices of nodal degenerations. You can try to understand those again in this nodal Hitchin framework. More generally, you might be more optimistic and ask if you can bootstrap the geometry or the topology of the Hitchin system using some basic building blocks and rules for nodal degeneration. So this is something that's commonly done in the physics literature, but it's not at all obvious that you can do this from a mathematical point of view. For example, take the metric on the Hitchin system or topology of the Hitchin moduli space. Are these things sort of amenable to some kind of bootstrap? Can you understand these for some simple objects like 3-punctured spheres? And are there rules that tell you how to put these together for more complicated Riemann surfaces? Our hope is that this nodal Higgs bundles framework would help in doing something like that. And this, of course, the general case of the Deligne-Simpson problem. I already talked a bit about that. From a mathematical point of view, you can also imagine trying to come up with compactifications of these Hitchin fibers in the nodal limit. That's again something we are thinking about currently. You can, of course, take all of these questions, the ones that we have answered and not answered, and you can imagine extending them to other Cartan types, or even more, say, adventurous question would be to extend all of these to wild Hitchin systems as well. Okay, so I'll end with this, and I'll be happy to answer any questions. Thank you.
Okay, thank you very much. Questions from audience? I ask lots of questions during the talk.
No, questions are great. Questions are great, especially when we're doing things virtually. Questions are absolutely great.
Okay, can I ask a question?
Yes, please. Yeah.
Yes, Krabbe-Bobby has a combinatorial criterion for the Deligne-Simpson problem. So in terms of root system, how
Yes.
this condition is related to this your OK condition?
Yes, so that's a great question. So we can translate, so basically you take, so this was a condition coming from 4D n equal to 2 theories. So you compactify these theories down to 3 dimensions, and you do 3D mirror symmetry. So it turns out the 3D mirrors of all these type A classes theories are certain quiver gauge theories. The underlying, say, dimension vectors that you get in these quiver gauge theories, the dimension vectors for the quivers, they are exactly the dimension vectors that Crowley-Beauvais would assign to the star-shaped quiver that he constructs out of the data for a general Deligne-Simpson problem. So you can show, at least in several examples, that the OK condition is the same as the set of conditions that Crowley-Beauvais et al. Have. Uh, but where there's a little bit of uncertainty is whether the necessary part of those conditions has also been shown. So there, I'm actually a little uncertain about what is the sort of state of the art in the mathematical literature. But that's the sort of sequence of connections. You basically take the OK condition for the Hitchin system, you translate it to a condition for these 3D quiver gauge theories, and then you check with whatever conditions Crowley-Beauvais and collaborators have.
So which is stronger?
Uh,
Even that is not so obvious.
it's not obvious. So there are some cases where I don't know if the Crowley-Beauvais conditions are necessary. So that's why I'm unable to say for sure if one is stronger than the other. It could turn out that that's the case, or it could also turn out that they're actually the same. That's still uncertain.
Okay, thank you.
Yeah, thank you.
Any other questions? You didn't use the pen and the paper
Oh, yes.
you prepare.
Yeah, I mean, my tablet has a few bad pixels, so I wanted a backup plan in case I wanted to write something.
Okay.
So, but
Can
yeah,
you
I can
explain
definitely-
something about this kernel bundle, kernel line bundle you constructed?
Ah, okay.
Yeah, I couldn't follow that part, to be honest.
Okay, so let me maybe go back to
Yeah.
the definitions. Okay.
Yeah.
Okay, let me first motivate them in the following way. So imagine you have this bigger Hitchin system on a smooth curve C,
Okay.
and that is factorizing, say, at some separating node into
Yeah,
some smaller
two
Hitchin system.
curves. Okay.
Right.
With double
So
point
I
or
want to
something. Yeah.
identify the analogs of LKs for these smaller Hitchin systems.
Okay.
Okay. Now, I'm sort of telling you the right algebraic geometric way to do this. It's to take this sheaf LK on C, think of the restriction map to the right or to the left, and take the kernels of those restriction maps. So those will again be some sheaves, but you can naturally think of them as sheaves on just C left or C right. So if you take the restriction to the left, its kernel will be a sheaf on C right, and vice versa.
Oh, I see. I see.
So I'm
That's
telling you the sheaves that you get this way are the natural objects that replace LKs now for these smaller integrable systems.
I see.
So their sections would now be the Hitchin bases for the Hitchin system on the left and the Hitchin system on the right.
I see.
But that's not the only kind of sheaf that you can have. You can basically also just work with the sort of vanilla restriction of these line bundles to the left component or the right component of the nodal curve. And these two things they're off by this O of minus P. So this might seem like an innocuous thing, but this sort of turns out to play an important role. There's a particular choice of parameters for which only the kernel line bundles, or particular choices of residues in the punctures for which only the kernel line bundles pick up H1s. That's sort of a way to detect an arbitrary restricted node. But there's a further special class where even the restriction line bundles pick up H1s. Those are the non-regular nilpotent nodes. Sorry, non-regular restricted nodes. That statement is not obvious. So in fact, to give a clean mathematical description of the appearance of these non-regular nilpotents at the node, that was kind of our sort of first concrete question. That's the question we wanted to answer. This was sort of known by different calculations in the physics literature, but it was not clear if it could be given concrete mathematical meaning.
Okay.
Yeah, was that helpful?
Yep. Any other question from audience? Okay, if not, let's thank the speaker again.
Thank you.
So I will stop